If you've ever used a can of compressed air, also called a gas duster, to, clean crumbs out of your computer keyboard, you're probably aware that after a little while, the air coming out of the can, and even the can itself, get really, really cold. Like, cold enough they put frostbite warnings on the can. It's tempting to think that compressed air cans get cold because when the gas comes out of the can, it expands and thus cools off. But that's not exactly right. Whether an expanding gas gets hotter or colder, and how much hotter or colder it gets, depends on the exact manner in which the gas expands. And if we apply the relevant equation for normal gas expansion, we'll predict that the gas inside the compressed air can should drop from room temperature to around 100 degrees Celsius below zero, which is way colder than what comes out of a compressed air can. So the gas can't be expanding in the normal way gases expand, and here's why. That would be like cutting off the top of the can and letting the gas expand freely in all directions. But the gas is actually being squeezed out through a tiny valve. This difference is key. The gas passing through a valve isn't simply expanding, it's also being pushed through by the rest of the gas behind it. And that compression from behind gives the gas enough heat energy to essentially counteract the cooling from expansion, but not exactly. Most gases at room temperature do get slightly colder when passing through a valve. A good demo of this is to let the air out of a bike tire. The valve gets colder, but not crazy cold. Similarly, the gas leaving a can of compressed air cools a little bit passing through the nozzle. But this can't be the only contributor to cooling. I mean, the can itself cools off by significantly more than can be explained by expansion through a valve, and it's not like it's even being sprayed by the air coming out. No, the real cooling power is hinted at by the warning labels telling you not to shake cans of compressed air or spray them upside down. If you do shake one, you'll realize right away that it's not just gas inside. There's liquid in there, too. Liquid like 1,1-difluoroethane, which is a gas at normal temperature pressures, but a liquid once you pressurize it to around 6 times atmospheric pressure. And it's the essential component of these compressed air cans. Inside the can, 1,1-difluoroethane exists as both a liquid and a gas in equilibrium. Just enough of the liquid boils off to maintain 6 atmospheres pressure in the top of the can, a pressure high enough that the rest stay liquid. Because it's at 6 times atmospheric pressure, when you open the valve, the difluoroethane rushes out in a steady stream, blowing away dust and crumbs. But this then means that the inside of the can is no longer pressurized enough to keep the liquid from boiling. So more boils off until the gas reaches 6 atmospheres of pressure again, and a new equilibrium is reached, but slightly less liquid in the can. This is how the can is able to keep blowing a stream of consistent strength even when mostly empty. But more importantly to our temperature conundrum, changes from liquid to gas require a ton of energy, and that energy has to come from somewhere. Just like how the evaporation sweat removes energy from your skin, cooling you off, inside a can of compressed air, the molecules that vaporize, aka boil, are the thing that steals energy from the liquid and cools it off, significantly. Spraying out 10% of the contents will cool the entire remainder of the can by around 20 degrees Celsius. If it seems counterintuitive that a boiling substance cools itself off, look no further than the humble pressure cooker. Water normally boils above 100 degrees Celsius, but by sealing in steam, the pressure rises, enabling the water in the pot to remain a liquid well beyond water's normal boiling point, just like the difluoroethane in a can of compressed air. And releasing water vapor out of the nozzle of a pressure cooker lowers the pressure inside, allowing a bit more water to boil off as steam and lowering the temperature of the remaining water, just like the difluoroethane in a compressed air can. And if you keep letting off steam, eventually the water will cool all the way back down to its regular boiling point of 100 degrees. Just like how if you keep spraying a can of compressed air, the difluoroethane inside will cool all the way back down to its regular boiling point of negative 25 degrees. A can of compressed air is quite literally a 1,1-difluoroethane pressure cooker. And just like you shouldn't shake a pressure cooker or turn it upside down, unless you want to spray superheated water everywhere, cans of compressed air don't work very well sideways or upside down. Instead of spraying out gas, you'll spray out the liquid that was only being kept liquefied by the high pressure inside the can. So it immediately vaporizes and drastically cools down whatever it's contacting. Instant ice. Though difluoroethane can dissolve in water and is poisonous, so definitely don't use this ice for anything food related. In conclusion, the cause for the coldness of cans of compressed air can be clarified by comprehending the consequent clue. They aren't actually cans of compressed air. They're cans of pressure-liquefied 1,1-difluoroethane, and lowering the pressure inside by spraying them allows more liquid to boil off, cooling what remains.